Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm super happy to have Braden Garretson with us today. Hey, Braden.
Hi, thanks for having me.
Well, thank you so much for agreeing to talk about your really lovely research note. I think it's fantastic. 10,000 light curves, which we'll get to. That's a lot of light curves. Awesome. Braden, what's your geolocation? Where are you at?
I'm in West Lafayette, Indiana.
Indiana, very cool. So is that an Eastern time zone, Indiana, or a Central time zone?
Yeah, it's Eastern time.
Okay. Snow on the ground?
No, well, it snowed a little bit, but not really much got on the ground. It's pretty cold though, about 18 degrees.
Ooh, not enough to make snow angels. Right. So this is January 6th, 2022, as we are recording this, as we're in the new year. So what is your position there in Indiana?
I am a sophomore undergraduate.
Oh, yeah. Very cool. Very cool. So you have about another 2 years to go, and I imagine hopefully next one will be another research note, or you get a second research note, or even a refereed paper, APJ, APJL, something like that. That'd be really great. So do you have any plans at this point to carry on, go to grad school, or you want to go into industry, a startup, something like that?
Yeah, my current plan is I want to go to grad school and go into research.
Okay, cool. Well, very nice. Keep my fingers crossed. Be really great. Awesome. So Braden, so far in this early start in your trajectory, what do you like to do for research?
Mainly what I've worked on is sort of machine learning applied to transients, mainly just supernova. That's mainly what I've done so far.
Machine learning is a very popular topic these days. And that is going to bring us to this very lovely research note. Supernova Galaxy Association and photometric classification of over 10,000 light curves from the Zwicky Transient facility. And Braden, take us away.
So yeah, the main motivation behind this paper, so the Vera Rubin Observatory is going to launch in a couple of years. And with that, we're expecting a lot more data. I think it's like an order of magnitude, or at least, of more data. And the problem is with supernova classification and identification, current methods like spectroscopy take too much time. You won't be able to get a significant amount of the supernovas that we discover every year.
Okay.
And so because of that, we need methods like machine learning to be able to classify a lot more of them and identify supernova rather than getting such a small portion, because otherwise there's a lot of wasted potential there.
Very cool.
So in recent years, a lot of papers have tried to, apply machine learning into the classification, identification of supernova. One thing that I noticed a lot of these papers didn't do is, and part of the reason why we did this, is they tried a bunch of different methods, but none of them were applied, at least specifically to ZTF, besides I think Alerce for the most part. And there wasn't any large data sets of what ZTF's done, at least that I've seen. And the main purpose of this isn't necessarily our classification, but just to get a big data set for more sophisticated classification means. So that was kind of the purpose behind that.
Very cool. Very cool.
So we got our data from the Bright Transient survey, just basically used all of the already classified supernova that we got from there. And then basically what this paper is kind of an amalgamation of different methods that I've seen in other papers.
Okay.
So, like Gaussian process regression, the wavelets, those all came from different papers.
Okay.
And it actually worked surprisingly well. We got about 80% accuracy across the board.
Okay. And what is the limiting factor on that accuracy? Is it just strictly number of photons, or?
It's usually the main problem usually is the data being, sparse and incomplete.
Okay. Mhm.
So when you're looking at the light curve, if there's,
3 points.
large sections missing,
Right.
it becomes problematic because a lot of the supernovas have overlap in their shapes. So sometimes type 1A supernova can look very similar to type 1B C.
Yeah.
For example.
Okay. Mhm.
Or you could be missing the section where it's very obvious what kind it is. That's usually the problem. And the way that you get around that, at least partially, is through Gaussian process regression, which basically interpolates the missing data points and is generally, it's pretty useful in estimating what it should be. The other main part that we added in this paper was host galaxy association.
Yes.
And I did that through basically repurposing Ghost, which was done by Gagliano in 2021.
Yes.
And originally we wanted to try to add galaxy information to try to further constrain the classifications, because that's another thing that I'd seen done, but not necessarily applied very much to at least large sets of data. We didn't get very much use out of it. It's probably because our data set, like other ones, is like the training set was kind of small and pretty biased. I think it was around 2000 something supernova in our training set, and most of those were type 1A. And when you have that many type 1A and then you only have around like 30 or 40 superluminous, a couple hundred others, you can't necessarily actually use the host galaxies association to learn anything, at least for training the model.
Okay.
So that's something that hopefully we can incorporate later, or someone else can take this and go ahead and incorporate.
Yeah. Okay.
For the classifier, we went kind of basic. We just went with a random forest classifier. And that went pretty well with the features that we decided to use. I toyed around with going the neural network route, but this was a lot simpler, and we got pretty good results for what it is.
Yeah.
Compared to a lot of other papers out there.
Sure.
Ours is somewhat. The Lursay paper for their classifier does the same thing, except they use a lot more features than we did.
Okay.
So yeah, the primary ones that we used were the wavelet features, which was reduced using principal component analysis.
Indeed.
And then we also used, the length of the light curve, the area under the light curve, how tall the peak is, stuff like that, and we were able to get about 80% accuracy. Like most, it was most accurate with the type 1As. And then we compared it to the Lursay classifier.
Yes.
It appears to do better, but there's obviously some caveats there. Our training set was bigger.
Right.
We to test, how accurate it was, we did cross. I forget how many full cross validation.
Right.
Where you split up the data set, so you try to eliminate any missing very important events since it's so small. And because of that, there could have been more variance in theirs, which doesn't necessarily mean, it's necessarily worse, but at least from our testing, ours appears to be at least somewhat better in some categories.
Competitive. Right.
Competitive. It's on par, I'd say, at least.
Very cool.
And using that, and we were able to collect about 13,000 supernova, and we did that using a Lursay's. So one of the Lursay's classifiers identifies what general class of object is. So whether it's like variable, supernova, AGN, the more general categories, and using that, we took a cut of those that had a 0.7 probability according to the classifier, and just basically pulled all of the supernova with that. And then we repurposed Ghost to tell whether or not the host was a star.
Ah, okay. Mhm.
Because part of what Ghost does is it tries to throw out, what are potential stars within the frame. Because that's part of the way it identifies whether it's which the host galaxy is.
Yes.
And using that, we were able to throw out a lot of the impurities. If I remember correctly, we got it down to, I think like 5% of the data set we know is wrong, which is pretty good.
Yeah, it's a
considering, especially how it was before.
contamination to remove, definitely. Okay.
So yeah, with that, we were able to get about 13,000. There's definitely some misclassification in there, as expected. We compared it to the spectroscopic sample from BTS.
Ooh, right.
Definitely overclassifying in some categories, like basically all the other papers on this. So superluminous, there's more of, that's mainly certain types of type 2 it thinks it's a superluminous. Obviously type A and type 1 BC is the big one. Those usually get overly represented because they get confused.
Relative, right. Yes.
But overall, I'd say it was pretty decent for what it was. And with that, we created the data set, which gives our classifications, Alerce classifications, the host location, any known spectroscopic classification. And the hope with this is, that other people will go on and use this and try to train more sophisticated means than ours.
I see.
Because there's definitely, the way we did it was kind of like a simple, straightforward approach. But I think there's definitely potential with some of the methods introduced in other papers. I know there's the Villar classifier,
Yeah.
which was, that's a potential route. There's also, I remember, I think it was the Boone paper. There's a Boone paper where they basically they created new light curves by augmenting the ones they already had, and then trained the classifier on it.
Yeah, right.
With this many light curves, I think that would be a very good route to go down, especially just because there's so many. And then there's other things like the other thing at Purdue, the other big project is refit, which is a recommendation. It's a recommendation algorithm basically. And that was one of the other motivations for this paper, is to get a large data set to train that. And what that does is, it's called refit. What it does is it looks at supernova and it tries to predict how they're going to evolve over time. And then tells you when the most optimal time someone should take data at. Because one of the problems with, especially going to be problems with Vera Rubin, is that it's taking in so many bands. It's going to be a lot more sparse than ZTF.
Okay.
So that's one application of the data set.
Cool. Well, and people can get this data set. It's available in a machine readable version. Yep. And you've also got it on Zenodo.
Yep. All of the data is there. All of the code that we use to get it is there.
Oh, very nice. Very nice. Good. So we'll put a link to the Zenodo repo in the description below the video. Very nice. Very cool. Well, Braden, thank you so much for walking us through your very lovely research note.
Thanks for having me.
Sure. So you touched on it a little bit there at the end, but let me ask a little more directly, is where do we go in the future? Let's say over the next 2 to 5 years, is there going to be a catalog 2 with 20,000 supernova from ZTF? Will it be augmented with other data? You mentioned a little bit about VRO and its applications there. But just sort of where does this go, let's say over the next couple of years?
Yeah, we definitely want to keep updating it as time goes on. I don't know how often it'll be updated, but we'll definitely update it. When Vera Rubin comes out, I don't think it'd be that difficult to augment the code that we have here to, be used for that.
Mhm.
And with that, a lot more supernova are going to come. Like I mentioned earlier, we're definitely going to apply this data set to refit to help improve that.
Mhm.
Beyond that, specifically to improve the classifier, I know that one thing we are looking at is, since we know the location of the galaxies, is using photometric redshift estimates
Mhm.
to improve classifications.
Mhm.
We considered using, redshift in it, but one of the problems with that is, it's usually not available, especially if it's not spectroscopically classified. It's not always available.
Right.
So that would make it difficult to train, but using photometric, that should be an avenue that we can hopefully improve it with.
Let me then ask a question. Do you foresee a day where you could get the classifications from photometric data, let's say at 99% instead of 80%? Do you see that as a possibility, or is that sort of just out of reach?
I'm not sure, because it depends. It depends on what your data looks like,
Okay.
because when
Okay,
you're like,
sure. Uh-huh.
it's very different looking at a light curve, like depending on how much data the light curve has, it's
Mhm.
very different on the, how likely the classification will be.
Got
If
it.
you only have like a couple of data points, and
Got it.
especially if they're like close together, I don't think it's possible. But just because of the error even in the results like itself. But if you have kind of like, if you had more complete light curves,
Mhm.
or at least ones that can be fixed using like Gaussian process regression,
Mhm.
I think that you could probably get into the 90s eventually.
Okay.
But you'd probably need more information than just light curve, I would guess, on sometimes.
Okay.
Because there's definitely circumstances where, like with the type 1A and type 1BC, could be, it could be dust
Mm-hmm.
or a variety of factors, or just the way that it looks in general.
Yeah, just be
That's going to make them look almost identical.
okay. Cool. Cool. All right. Well, I look forward to seeing this project evolve over time. I look forward to seeing version 2.0. I look forward to seeing the next paper, and that will do. And I want to thank you so much again, Braden, for walking us through your very lovely research note.
Definitely. Thanks for having me.
And that'll do, everyone. And I hope this makes your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.